Are you staying?
Yeah, he just for introducing.
Why? You can go and then I can introduce if you have something to do.
No, I will go after. Okay, no, visit you after 2, so I will leave after interview.
It's a choice, it's a choice. So it was okay. We had a lot of good morning, but the professor was happy and the participants too. Very staff, but I asked Momo to send because I asked them to have the main and producer. And I asked them to I think that the first day they were actually down and most of the people are still out of that. But everything is okay, everything else back to the way. You did great too. Your friends support you a lot. Supported a lot. Mona Lisa, yeah. She was
Yeah.
I tried to do the same thing but you did not look at me. She was very active and supportive.
That's why I got.
Yeah, he seems to be your friend. So that's why I asked you, because normally I want you to take time to prepare everything. Yes. No worry. Don't worry. Don't worry about this. Be ready. What we prepare. There are 17. Yes, 1:30. What time is it? Of course, doing it. Don't worry, Una. Don't be so nervous. Yes, I will take care of this. Don't worry. I think people skip today because that is very basic one.
Yeah.
They focus on the industry day. But I will try my best to bring more people. I mean, that is not something that we can control.
Of course.
They registered to come, but they
So video it. What happened to the register you did the group?
that is something very typical French typical. The coffee. It is highly motivated, really. He told me, he planned to do on whiteboard, but he afraid that they are not to whiteboard. So he didn't sleep really. But we can see that he was our performer. Are you a data scientist? Are you working in Paris?
Yeah. You know Gently? Gently?
Gent-
Yeah, Laundry.
No, I don't. What is the name? Can you show me on
Sanofi?
Sanofi?
Yeah.
Yeah, I know Sanofi.
Yeah, Sanofi Gently campus. They have
Ah,
many like larger firms here and there. I work in Gently.
so you are the one who actually want to work on some projects
Yeah,
on Q
for sure.
can collab.
What are you working on right now?
So I'm working on so we have a community of 11 culture have a different background.
Yeah, I saw.
Yeah, you
The
see.
album.
Yeah.
I
Ah.
saw you in Cube-Land Hackathon. You won, right?
Yeah.
I won in the QML.
You too.
Yeah, the QML track.
Ah, you won. Wow, congratulations. Yeah. She won it.
Yeah, and I saw your team.
Yeah, we have the
In
second
finals.
place.
Yeah, in finals.
Because we were so busy, we had to organize it in the same time. And at the same time, we have a quantum hackathon. Congratulations. How are you? So you know all of this thing.
Not really. I'm very intuitive. Like on the if it's machine learning side, I adapt quickly the concept. But I want to learn the basics now. My foundations are physics. I come from business and math background, so I want to learn physics. Just like make my
So you
foundation.
come to the right event. So okay, so we work on many projects. We have three big teams. First one, that is technical project. Second one is organized event. This guy. So that is our first event. If there are some mistakes, please. That is our first event. Please understand.
And I think you were the first to organize in France, right? I've seen many Qiskit and for Western countries. I haven't seen France.
Yes. So
yeah.
yes.
But
So I'm very proud of my kid. Yeah, so you can see I work so hard to have it, and we're very happy. We try to bring as many participants as possible and give free access to them. So we celebrate for 100 years and so on. The other event try to charge people,
yeah, they charge us
but we don't. I don't want to charge people because first of all, that is our first, but it's not only the reason that we do not charge. We just want to bring as many people as possible to connect all of them to bring the future collaboration as possible. So that is our main idea. It's a more time. Oh my god. How to go here?
Or speaker virtual? Speaker's virtual, okay.
Ah, it's coming, it's coming. Coming.
Okay. Okay, so you put that.
Mostly it's you. Does you want to share in the screen? Share the screen. You can start. No, it's fine because Mona Lisa will share.
Does Mona Lisa has the access? What's the ID of Mona Lisa so I can give her the access to share?
She's there in the room.
She's in the room. So
I'm here. I just don't see a share option.
I will give it access to share right now. Yes.
So welcome back, everyone. In this session, the first speaker is Dr. Manasa Singh Roy. Dr. Manasa Singh Roy is a quantum physicist and a quantum algorithms engineer with a strong focus on real-world optimization using quantum and quantum-inspired classical techniques. She earned her PhD at SN National Center for Basic Sciences in Kolkata, where her research explored interactions, correlations, and competing orders in strongly correlated one-dimensional quantum wires and quantum gases. Following that, she completed her postdoctoral fellowship at Bar-Ilan University, Israel, investigating quantum many-body physics, dynamics of quantum information, measurement-induced phase transition, and quantum chaos. Currently, she is working at Planck in Munich as quantum algorithms engineers, developing quantum digital annealer and tensor network-inspired algorithms for applications in finance, logistics, and other optimization problems. I have the pleasure of knowing her for over a decade now. So today she'll be speaking on hiking the quantum landscape, BQE, QA, counter-diabetic corrections and portfolio optimization. So let's welcome Dr. Manasa Singh Roy for the nice talk. We'll have the pleasure to listen to.
Thank you so much, Poonam. I'm very grateful to all the organizers, especially my friend Poonam, for giving me the opportunity to speak here. And it's an absolute pleasure. And let me show why it's such a big pleasure for me once I'm able to share my screen. Like, guys, is it supposed to appear on the screen I see there?
You are able, I think, right now. You have the access.
Yeah. Yeah, but is it supposed to appear on the screen I see right now? Like or will you guys just be able to see on your laptops?
Try to share your screen and we will see, yes.
Okay. Let me try. Let me know if you guys are able to see this.
Yeah,
Yes, okay, good.
You see this? Great. So thank you so much for inviting me here. It gives me a really special pleasure to be here. Let me explain why. So let me start by saying, yes, my name is indeed Mona Lisa, and it's indeed inspired from the painting you have in your city. It's actually a favorite painting of my parents, and I'm actually named after it. So now that we understand each other, let me again thank the organizers for inviting me and giving me the opportunity to talk to your student community, to you guys, and share my excitement about all the things I think quantum can make better. We have to pick and choose, but let's see. So a bit more about myself, as Poonam already said. I'm from India and in the eastern city of Kolkata, where I did my PhD in very traditional condensed matter physics, strong interactions and stuff. It's actually not that far away. You can see only 14-hour flight. So after I finished my PhD, then I went on to do my postdoc with Professor Jonathan Ruckman, Emanuele Dallatore, and Efrat Shimshoni. It's very likely that you might know only one of them because they are from very different fields. Jonathan is very good at something called measurement-induced transition. Emanuele is known for quantum information and also quantum circuits and quantum computation. Efrat is a superconductivity person. So you can see I come from a very varied background, like I'm guessing the crowd to be today. So I'm one with you. I wasn't born expert of this quantum way of doing things, but we will see how it can help us in our algorithms as well. So right now I'm based in Munich, not that far away from you actually. So I'm part of Planck Gamba's algorithm team in the northern part of Munich actually. And our company has recently been making news because we have got some very exciting projects in which we plan to optimize the routes for different transportations, also construction of certain materials using our neutral atom quantum computer. That's on the hardware side. But the algorithms team is actually the biggest there, and many of us work on optimization problem and provide support to all these projects. And we are a happy bunch. And if you're ever interested, drop us an email and we will see how it goes. And this is the algorithm team, at least part of it. So you can see how we are managing the projects. There are many of us. Okay. So now that my talk is the first one after the lunch, I thought what could be better other than hi to digest all that food. So the root for this talk is understanding the quantum landscape and how we formulate the problem itself. Then to discuss the variation strategies to solve a particular goal in this quantum landscape. And from here, we will go to QAOA and CD correction if time permits. And then we will try to visit at least one optimization problem and see if these algorithms are any help or not. So stop me wherever you feel I have rushed through. Don't let me proceed. It's your talk. So let's make sure all of us go together in this. So, okay, let's start our post-lunch hike. Let us imagine for a moment it's a bright afternoon. I don't know about Paris, but in Munich it's not bright. But okay, let us imagine it's a bright afternoon and we are a group of tired but enthusiastic visitors overlooking a panorama of mountain and valleys. Okay, and for whatever reason, we decide we want to find the lowest valley in here. We will come to later why this is a rather cool and common problem, trying to find the lowest valley. But for now, let's consider a nice bet. Who can find the lowest valley the fastest and with lowest efforts? Now, know this, from where we stand, there are several valleys which look like good candidate valleys to be the lowest, but it's impossible from here to know exactly which one. I mean, there are low valleys, but which is the lowest? That is what we want to find out. And daylight saving has started and it's a post-lunch hike, so we have limited daylight, limited energy. So with all these in mind, let's see how we can navigate to the lowest valley, which is our goal for today. We have to find the route, how to go from top here to the lowest valley. Okay. So here are some things we need to know because remember, we are a big group. So in order to do it in a disciplined way, we need a strategy. And for that strategy, there are a few knobs we can work with. Maybe we can decide a stride length, how big steps we are going to take. And we can decide how we will just make our balance, where do we place the pole. And of course, we have a stopwatch in which we are checking our speed, how much time has elapsed. And we have a couple more tools But remember, they are not the most accurate. So there's an altimeter which tells us how high we are. That is how we would know when we have arrived at the lowest valley or not. And we have a rough, outdated map. Maybe natural conditions have changed and it's not accurate. So, with these in mind, let's begin our hike. Since we know nothing at this point other than a vague line of sight, what's the first thing we would do? Probably we will break into groups and we will try to climb down, set a time that, okay, we meet after 30 minutes. Let all the groups go for scouting rather than the group going together. We want to collect data. So we pick a trial value for all these knobs. Maybe we choose a medium stride length. Maybe we are placing the pole in front of our feet every time. And of course, we are looking at the watch and keeping our pace moderate. Now, as we descend from one candidate valley for a short segment, we keep recording the altitudes, how high we are, and we also keep note of what are the trial, pace, stride, pole placement things we chose. So we are doing this in the disciplined way. If any of the audience was in Scouts and Guide, they can correct me if I missed anything. Okay, so we do this and then decide to return to where we started from after a certain time, and then match our notes who did best. So we record the altitude loss per unit effort. For example, how many people slid down while doing that. So you get the gist. We are trying to collect data for various routes, come back after the recon and compare notes because we have really no idea where the valley is. And we have to do it many times because the readings are not always correct. You have not always taken exactly the same stride length. There are various sources of noise. So after each scouting trip, we record our measurement and change these parameters a bit to find out if we do better. Maybe the ground was firm in one direction, so maybe we did not use the poles. Many things can happen, but let's record everything. And we try to repeat the same thing a few times for getting a good average. Now, as we keep on repeating this process, probing a bit different route every time, we are slowly collecting the data for all possible trajectories we could take. And after several of these scouting trips, a pattern will start to emerge. Maybe the eastern side is easier to walk on. Maybe there are places we can actually run because they are flat. Maybe there are some small hills where we need to slow down. So you will slowly start getting the gist of the landscape a bit. Like not in super details, but at least in coarse details. And you will also see that your pace is changing. For example, you're faster on level ground, but you should go slower whenever there is up and down. So you will start having an intuition, let's say. Physicists don't like the word, but let's use that. So soon enough, we will be falling into a particular pattern, which now, because remember, different groups went for different scouting routes. But now, because the pattern has emerged slowly, you can tell the other group that if you follow these movements in this sequence, you reach there. And they're able to follow your instruction. That's a sign that now you have logged in your series of good number of parameters and the sequence. It has become repeatable. So this is a good sign. Now you're getting closer to your valley. So at this point, we do it enough times. Not only have we identified good routes to move forward, we kind of know where approximately the lowest valley lies. Because on our scouting mission, we have gone to different valleys. We come back, compare notes, and somebody will have gone to the lowest valley. So now we all can go with them, that group which found the lowest valley. So this, my friend, is the essence of variational quantum eigensolver. We start by scouting various trajectories from an initial point we can decide on. And as we do the scouting, every time we make a bit of variation. Maybe sometimes we choose to go more right, more left, slow down, pace up. So we start making those mental maps. And of course, we have to measure, keep a record of everything because that would inform our next scouting mission. So it's an iterative process. And finally, as we go about collecting more data by averaging and recording, we eventually go to lower and lower values. So that is the essence. But keep in mind, we have limited daylight and our energy is not infinite. Not all of us are superhuman hikers. And our measurements might be noisy. So this is a kind of snapshots that we are working under constraint. We have to benchmark ourselves, and every scouting mission takes us closer to the best valley we have explored so far. So this is the essence of VQE. So everybody with me so far? Nobody lost on the hike?
Everything is
Assuming it, sorry?
So to go to the valley, like we have to do this, like these shots, like we have to do it like in parallel or one by one.
That's a very good question. Let me answer that 2 slides later, but that's a very good question. Thank you. So, but let me give you a hint of an answer because there are so many of us in the group. If there are some paths we are not going to overlap on, we can also do this in parallel. But we have to see what kind of overlap we are talking about. So now, before we go further and formalize this, when I said that we need to get a lay of the land, since most of us are physicists, we have to have a more definitive framework of what's the lay of the land. Here comes our friend, the Hamiltonian. Hamiltonian is something which tells you about what are the paths your system can exist in, what is the landscape of the system, how high can you go, which directions can you take, which are allowed ones. So formally, if I am to formulate a Hamiltonian for this problem, I can think of different distribution of heights here in the z direction. And we can use Pauli operator to give us choices. Like we can, because let's assume we are going from the eastern side to the western side. That direction is kind of fixed. We can decide maybe the operator tells us to go left or right. So that's the problem we are going to be working with now. We have a description of the landscape. We know how high it is at each point. It tells us what are the allowed direction for us to travel, left or right. And our goal would be to scout many of these paths, like left, left, right, and quantify the total energy it cost us. And remember, we have the height profile here. So each classical route we take can be defined as the energy you calculate as a function of all the sequence of your choices. It could be sequence, or it could be where you reached in the end. And our goal would be to find the ground state of this Hamiltonian, which corresponds to the lowest valley. Okay, so we are trying to find in this particular language the best route to the lowest valley. So let's revise what we did as our scouting group. What we are doing essentially is each time choosing different kind of operations on our initial state So say we started from the highest point anywhere, and we can assign a quantum state plus state on all n qubits. In this particular language, each qubit can correspond to each of the points en route to your valley. So maybe we started from one sample route and we started checking what happens if we modify the path a bit. We can calculate the energy cost of this trial route for each of the choices we make through this parameter theta. Theta could be your speed, could be how long you're taking your strides. It could be your pole placement, anything. Point is, this is all of the different choices you can make. And as a consequence of those choices, you measure this cost of the trial route. Now, since we said we want to find the lowest valley, it stands to reason any valley you find or any cost you find for your route will either be greater or equal to this valley. Okay, this is important. Why? Because now you can make sure that all the paths which you traverse are taking more energy cost than the previous one. You can keep discarding. So now you're collecting the best paths already. So now if I am to state this entire journey we took a bit more mathematically, what we do is we have this fixed number of amplitudes at each of these points, Z1, Z2, whatever. And we can explore one parameter at a given time for all of those different Z operators which we have in the system. So we will cross a total of n points while trying to get to our valley. And for all of those endpoints, we can make slightly different decisions. So that is parameterized through this gamma. And maybe we want to decide how we are going to do it. In this problem, there is just one Z operator, but maybe you can use a different combinations of operator here as well to create some variation that will give you other kind of mapping within your choice of route itself. So it's like you can design the entire path, but deciding to do it with different kind of movement, vertical movement, sidewise movement. So you have got all these flexibility. But now we will also have something called a mixer Hamiltonian. Say you take a specific angle turn. So here it's parameterized by Pauli X operator. So you see already we have two kind of different operators. This is X and our problem has V. So it allows our paths to interact, be interesting. And each of our trajectory downhill now is just this set of two operators, the mixer operators, which is the X gate, and the problem operator, which is simply the Z gate. So if you wanted to describe an entire route for each scouting group, it's this. For your choice of parameter theta, which is how much Z rotation you did, how much X rotation you did in your first step. In your next step, how much Z rotation you did, how much X rotation you did. In your next step, like this, at each step, you decide how much rotation in what direction, and this gives you the entire route. So as we go further, after certain checkpoints, we will keep measuring. We need average over many measurements to see what's the total energy cost for each set of choices we made, each choices of which direction to turn at each point. And of course, we will try to stick to the paths which give us the lowest cost. And we try to make a variation on the lowest cost at each time. So after each iteration, we record these values, and then we decide how much to deviate from that. And all of these we do keeping in mind that we can do a fixed number of iterations, a fixed number of total shot per measurements, and there's only so many of steps we can take. So this is a bird's eye view of what variational quantum eigensolver is all about. And if I am to summarize this in 4 sentences, it's simply choose an initial set of parameters. For example, for this guy standing here, always choose to go left. It sounds stupid. Yes, maybe it is. And then maybe you can build on that, take left, 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 left route and decide to take right sometimes. Measure how far you have gone in terms of depth, your energy it has caused, and then choose a better parameter next time. And we keep repeating this until we have found, given the total time, we have found our best possible estimate for the lowest value. That's it. That's the main physics there is to it. So congratulations, you have finished your first hike already. So in terms of circuit, just to have a visualization, because many of you might already work with Qiskit, it's like starting from an initial state. All qubits are 0 here. You can apply Hadamard or something. And you can here apply n layers of gates and then see how far you have come. You can make a measurement of this cost. And then based on the results, you can optimize the next iteration of parameters theta. So we keep doing it iteratively as much as we can, because usually if you're running it on a hardware, you can do only a fixed number of layers here. And of course, how big strides you can take, how big you can take your gates, and um, total number of gates you can apply at one go, all of these are going to be limited. So very much like our hikers, limited energy, limited number of times we can go down and up. So this is our snapshot for the VQA algorithm, and this is actually a very good reference if you want to read more about it. So, okay, that was not tiring at all. So if you guys want to take a moment or ask me more questions at this point, this is a very good stopping point. Yeah.
One more question, like how you
Yeah.
can prepare your state psi theta? So there is a specific method or
So generally, let's again look back at our Hamiltonian. Because remember, our problem formulation here is defined in terms of how high each point is, because it's a rocky terrain. So depending on your problem, usually they are in the z basis, usually. But depending on your problem, you would like to make the measurement in the basis the problem is formulated. Because here, for example, you will try to formulate in terms of the best route you take, like left, right, whatever. It's parameterized through the parameter z plus minus 1. In your case, if the problem, for example, is defined in x direction, then you can either map it back to the z direction, which is better because usually Qiskit uses z basis as the base, unless you do something fancy and change it. So generally, all the classical registration bit where you measure are in terms of z direction. But it's generally not a problem because even if your problem is defined in some other basis, you can usually do some kind of transformation. But by default, you generally measure in the z direction. But then again, the main thing is how you describe your problem. You will try to always phenomenologically create your problem in such a way so that your solution also lies in the z basis. Yeah. So, but if you have some special problems in mind, maybe we can talk about it after this. But rule of thumb, z basis. Okay. So any more questions, or are we ready for the next hike?
Ready?
Next, great, amazing. Okay, so for the next hike, we will actually build exactly on the VQE algorithm we just developed, and we will just put some additional information on it. But before that, I would like to talk a bit about quantum annealing, because I'm not sure about the background of the audience. Let me just take a quick detour. So, what's the one theorem we need to remember is that if we start from a quantum uh, system which is at its ground state and slowly modify the Hamiltonian, then adiabatic theorem states that it will always stay in the ground state throughout this evolution, provided it's slow enough. And only just remember this picture that we are trying to go from one state of holding something to slowly changing it. Slowly being an important word. We will see why. So, with this idea, what we want to do is we want to start from a ground state we are very familiar with. Because remember, we don't know this terrain or landscape very well. So we want to start from a Hamiltonian we know. So this X Hamiltonian is very nice in that sense. Most of you who have done these eigenvalue problems will immediately put the guess eigenvector as all the spins aligned in the positive X direction, which is simply our previous choice of initial state. This one, this is the ground state well-known solution for our mixer Hamiltonian, which is minus X direction. And because it's easy to create, it's a product state, it's easy to create on most quantum computing hardware. And from here, we want to create this problem Hamiltonian, which can have both Z or ZZ terms. And we want to do it slowly. So when I say slow, there is this parameter lambda t, for example, which starts at 0 and goes to 1. So initially, all our spins are directed along the positive x direction. And finally, we want to simply reach at the solution, which we don't know what it is yet, using the adiabatic theorem that since we started from ground state, we go slow enough, we will reach automatically our intended problem's ground state. But some of you might already be asking yourselves that how do we make sure that we are staying at the ground state? How do we make sure that we are slow enough? What is slow enough? So, one line answer is you are slow enough if the time evolution is happening in intervals which is bigger than inverse of your lowest energy gaps in the system. It's just a technical line, forget about it, but just keep in mind this is a valid question. How slow is slow? Generally, we do some hit and trial when we are optimizing on the circuit, because if we are that slow, we will have to apply many layers of the quantum circuits and infidelity keeps piling up. So in short, we can't afford to be slow always. It's like your daylight time is going, we have to reach the destination. We can't always afford to be slow. But what happens when we move too fast, which is naturally the scenario? We can spill the water, there might be unintended transition in the system between this starting mixing Hamiltonian to the final Hamiltonian. We might induce perturbations we don't really want to. So for that, there is this nice idea which was floated a decade back. It's that, so what it says is it's not a problem if you move fast as long as you compensate for the errors you caused. So these errors they are talking about are diabetic transitions. So diabetic transition is when you move something fast enough, you create heat in the system. And you guys remember what happens when you give heat to quantum system? Some transition from lowest energy to high energy just happens because there is free heat. So what we want to do instead is for every accidental heat we give in the system by perturbing it weirdly by going too fast is to cancel out the heat in the opposite direction. So whatever error you caused, you just subtract it. Easier said than done? Yes, easier said than done. But keep in mind the idea. We will see how exactly they do it. But all we want to do is if we are going faster than we should compensate. And if you need a visual picture, then if you're driving your car too fast and you have bends coming, you have to compensate for that higher speed. You have to start turning already rather than if you were going slow. So with this in mind, let's build on the picture of VQE we already have by now. So in VQE, we were carefully scouting, going in groups, checking out different trajectories, lock the best trajectory, and then try variations on that trajectory to reach the lowest valley. But in QAOA, it's a more structured approach. So what we want to do here is fix the number of steps we do and specific step length that we are not varying. But what we are still varying are these values of gammas and p's. So now the prefactor we had theta has become very specific. There is small shorter steps you're applying, and you're applying p number of times, but you can still vary these two angles, the x angle and the z angle. And again, you check out these angles, you record the result, use classical optimization to make a better guess now. So it's just a more structured way of doing VQE. So here is a brief snapshot. We again fix the number of layers we are going to do for this iterative process, not iterative because now we apply one after other. We can start from an initial guess for these two parameters. This is our problem Hamiltonian bits, and these are for the mixer Hamiltonian in x direction. With these initial guess parameters, so you notice there is a subscript p, because now we have fixed that we will do it only p number of times, and it's our initial guess, which is 2p parameters. So with the 2p parameters, we measure in z direction. Where have we reached? And we do enough number of shots to estimate the cost function, the energy. And based on the result, we again use a classical optimizer to make a better guess of this entire parameter route. So how many times must we do this? You can try and do this until you reach a certain accuracy, or you might have hardware constraint of how many layers of P you can do, because remember your circuit is getting heavier. So the rest is very similar to the iterative process we just learned in VQE. So in VQE, while we could have parameterized it in any way we like, it's just a very particular ansatz. You apply your mixer Hamiltonian and your problem Hamiltonian in a very specific way, because initially you start with a lot of your mixer Hamiltonian and you try to end towards P with a lot of your problem Hamiltonian. So essentially, it's like time slicing. You go from this state, which you know very well, which is everything in x direction, and you chose different P time slices to reach to the final state you want to go. And now, at each time slice, you try to improve your rotation parameters. So that is the essence of QAOA. And as we discussed that we will try and even improve this, one way to do that is adding counter-diabetic transition. So how to do that? Let's first discuss that what is this diabetic transition? So when we are moving from the mixer Hamiltonian to this Hamiltonian, there is a mixing up of these energy levels of these two different Hamiltonians, mixing up which we do not like. So what we do is try to find out a way to nullify that. So remember that this mixer Hamiltonian was in x direction, all x gate, and problem Hamiltonian was in the z basis. So we might choose an ansatz in the y direction so as to nullify any transition which is caused by these two mixing. And there is a very specific mathematical formulation for that given by Michael Berry in 2009. But you don't even have to use that ansatz. As long as you try to nullify the effect of these two mixing, you can create your own ansatz. You can define that you will do CD correction in Y direction, or maybe you will use a 3-qubit gate, whatever you choose. The main point is choosing how much correction you can do. It's always choosing the coefficient of your correction. So this is what many recent works have done. So without going into specific details right now, we will go into a bit more detail towards the end. The idea is to do, in addition to this Hamiltonian, also apply an additional set of gates we will call CD correction gates, parameterize it by other set of alpha rotation, and essentially keep doing this whole process. So we start going with this problem Hamiltonian. We also have this beta Hamiltonian corresponding to the mixer Hamiltonian. And now we have put this layer of CD corrections. So we will again make a trial trajectory, measure all of it, compute the cost function, and then optimize these three set of parameters corresponding to these three blocks: the problem, the mixer, and the CD correction. So that's the basic idea. And this is a very nice paper in which they described it well. Yes?
I have one question. Sorry, I
Yeah.
missed.
Yeah.
What is the role of UCD in this guide? Why do we need this?
Yeah, okay. Let's go back to this. So
Yes.
our adiabatic theorem tells us that we can start from the ground state of any Hamiltonian we like.
Yes.
And if we slowly change to go to a more complicated Hamiltonian, any other Hamiltonian,
Yes.
due to the adiabatic theorem, we will always stay in the ground state, right? If we go slow enough, adiabatic evolution. But when you're working with quantum circuits, suppose you can afford to have only 10 layers of shorter gates,
Yes.
because after that, your errors in each gate just gives you very messy results.
Yes. Should be-
Now sorry?
Yes, if we can go beyond 10 layers, it's too deep to handle with the quantum circuit, right?
Yeah, right. Then, for example, if classical computation actually sometimes does it better, but if you are still doing quantum computation, by the time you're on your 10th layer, it's a really deep circuit. So you really have here a budget of how many layers you can do. It also means that, because remember, your time evolving, you have to do this entire evolution in 10 time step, which means you are changing in bigger chunks. You are supplying more energy to the system. And that energy is taking you out of adiabatic flow. think of when your tap is going slowly versus when you have turned on the tap very fast. The flow is not smooth anymore. Your water jumps, splashes, it creates heat. It's that heat which causes you transition from the ground state, from your intermediate ground state to intermediate excited state. And once you're in the excited state, your adiabatic theorem does not apply anymore. When
Yeah.
you stop your evolution, you might have reached a step where you are not in the ground state. You are still in one of the eigenvalues of the problem Hamiltonian, but it's not necessarily the ground state. You are in one of the excited state.
Mm.
So formally, if you knew what your problem Hamiltonian is, and if you calculated the lowest excitation gap from the ground state to the first excited state, then you would want your time step to be smaller than inverse of your energy gap. If you can ensure that, then you will always go to your ground state. But that means you will take very small time step because it's a small number. For example, a Trotter amplitude of less than 0.1. So you are not going very far in your adiabatic time evolution. So it's to address this problem that you really can't go that slow. You try to introduce additional corrections. Like if you have to shake your hand too fast and your glass is wobbling, try to make sure that your surface is still touching the glass. And that is exactly what you do by introducing new corrections. Those corrections depend between your problem Hamiltonian and this Hamiltonian, and the choice is not unique. It could be unique, but then it becomes too complicated. Anyway, so you can choose to do some extra rotation with your hand to still stay close to the glass. And that way you will cause less spillage. You will still be able to make sure that the water surface is level, no matter how much you changed it to a new configuration. So that's the role of CD corrections here. So what we learned, for example, this is example of a specific correction using Y gates. And this is a very deterministic way of doing it. But then again, this is a very simple Hamiltonian. This example I have quoted here, this is only for nearest neighbor interaction. So this looks easy. Generally, the problems in real life you're going to be working on, all the optimization problem, will have a complex structure. So generally, people don't get to implement the exact CD term, they implement approximate CD terms.
Mm.
So, for example, in this particular work, they actually adopted a clever heuristic, let's say. What they did, they calculated the energy of the problem Hamiltonian due to this set of configuration for these parameters. And then they gave an opposite gate using this amplitude. But you see, this is also heuristic. So whenever you are trying to apply CD corrections to your problem, what you ideally want to do is look at what is the mixer and what is the problem Hamiltonian. Because for me, for example, it's obvious that if I'm working with X and Z, then I will do a correction with Y, or maybe Y, Z, Z, Y. Or people have even done it with triple Z. But depending on your choice, now you have to optimize this guy, how much correction you should apply, otherwise you again offshoot. So this is again an optimization task, but you do it the same way. You make your choice of trial parameters for problem block, mixer block, CD correction block, then do your then you do your classical measurement, use the classical optimizer, try a better value for these, see if your energy is decreasing or not, and that's it. So far, we have built a picture of what it really means to use a variational quantum optimizer using CD terms. And now next we want to apply it to a use case. So the use case we can pick, which is essentially a prequel to this entire exercise we did, hiking, because before we go for a hike, we have to pack our bags. And packing our bag means that we have to select a small set of useful items. You want to be safe, prepared, efficient, but you have limited space, you can carry limited weight. And maybe some things are just redundant, maybe you don't need them. So you have to make a decision based on what items you need and where you are going, so the environment as well. And you have to choose the set which works best for you. We will see why the you is important. But because you also have constraints, we call these kind of problems constrained optimization problem. So, for example, what are the choices you could make? If you are going to a high altitude like the Alps, you need a good jacket, high calorie food. If it's a remote area, you need extra water. There will be no signal, so carry a map. Is it going to rain? Are you going to stay overnight? Do you need a book? So, depending on the constraint and where you're going, you will have a checklist and you have to make a decision given the constraint. And many of them might be good decisions, but you have to see which are the best decisions for you. And then again, some decisions are interconnected to each other. There's no point carrying an umbrella and raincoat if you have limited space. If you're carrying phone, you of course need power bank. So you get the idea. Many of your choices are connected. Many of them interact. So some interact positively, like your stove and gas, you need both, but maybe you need either a book or an iPad, not both. So this is how we will start making an interaction matrix soon, but keep these pictures in mind, it will help us. But packing also depends on external environment, how sensitive you are. Maybe you like comfort, maybe you like to be prepared. So if we try to formulate these things more mathematically, that what is your risk aversion? What are the things you like to not carry? You don't like to carry copies of things. We can start formulating again a set which is less redundant and more diversified. And many of you might be hearing these words and already thinking of, wait, diversified, external environment, risk preference. Where have you heard this before? Probably in finance, in portfolio selection. Let's see how. So our problem of trying to select things to pack is very similar to if somebody says you can buy 20 stocks out of 50 available stocks, which stock should you buy? So what will you see? In packing, you see the usefulness of your item. In portfolio optimization, you're looking at how much return you get. Here, you want to avoid redundant items. Maybe you want to avoid correlated assets. If there's a metal company which is supplying metal to BMW, maybe you want just one of them because both of them might increase and decrease together. So avoiding such correlations is a sign of risk aversion. And where you had a constraint of volume and weight, you now have a budget constraint. And the things which are not in your control are, for example, the external weather. And here, the market works the way it works. You can't do anything about it. So you see, it has the same structure. You have to make your choice out of given options. You would like to maximize your benefit. We will try to formulate it as, again, minimize energy problem, which we just talked about. And we would subject it to constraint, of course. So let's see how to exactly formulate that problem. For now, we will not consider external factor. We will focus only on what's in our control. And we can formulate this in one line as choose n possible assets. Like you have n assets from which you can choose whether to invest or not invest. Remember, take right turn or left turn, and within a budget K. And what you can know is, of course, the expected returns. Remember the height of the landscape. Risk aversion, this was not there previously. This is to control how much related, interacting, connected assets you want. So given this, what's your best choice of assets? Or in the previous problem, what's the best route you can take to find the lowest value? So we will try to formulate this maximize profit problem into find the low value problem. So these are just some sample values these guys can take. But at the end of the day, this is exactly how we would write it as a Hamiltonian. We have a negative sign because remember, we want to create a minimization problem. So we will like to maximize our returns. So it's the main factor, and the corrections are depending on whether you try to take risk or avoid them. You have to consider how the assets are correlated to each other. And this entire thing we formulate as yes or no. Invest in stock I, yes, no. Invest in stock I plus one, yes, no. Like that. So we still stay in binary. And you might have seen we are back to our spin Hamiltonian, binary decision Hamiltonian. So congratulations, we are almost there. We have everything we need to know. Let's just see how to implement it. So the most trivial thing you can do for these kind of problem is exact solution. Check out by trying out each combinations of 0 and 1 and see which gives you the minimum energy. That's probably your solution. But that's very tedious. And we are here, the quantum people. But just before we go into the quantum one, keep in mind that these kind of problems are also very nicely solved using your quantum-inspired tensor network methods, for example. But what we will try to see, people have actually tried it out, is what does quantum annealing give us? Like it is slowest, but you at least know how far you are away from the solution. Because remember, the shortest step you need to take is inverse of the minimum energy gap. So for digital quantum computation, going through vanilla quantum annealing is probably not the best idea. So let's see what's the state of art we have right now in 2025. So it's still, as far as QAOA is concerned, this still is among the best results, in which people started from a mixer Hamiltonian, parameterized it for each beta values, problem Hamiltonian, parameterized all the gamma values, and introduced heuristic CD corrections. So here, let me just tell you about how they are calculating their efficiency. So here, remember that they calculated their prefactor for their corrections using the energy of the problem Hamiltonian for each of these values. So this is how they're checking how far away it is from the true ground state. So this is a very clever first benchmark, actually. Does not require you to give too much effort, but you can quantitatively see the results. So what they show is, depending on number of layers, you actually have your normal QoA result here. And remember, depending on the problem, your number of layers is limited. And while it might look a small improvement using CD corrections, it's an important one. Why? Because imagine all of your qubits are connected in your problem. It's interaction which is usually the costliest. So say you have 5 qubits in your system, then you have a combination of 5 cross 5 matrix of interactions. So if you have to implement that many gates, it's costly, very costly to apply each layer. So as you go into the adiabatic limit, which is more number of layers, Of course, these results converge, but if your problem Hamiltonian is very complex, even this much improvement is a lot of improvement. And remember, this is a heuristic value of counter-diabetic term. You can always try and formulate a better canceling of these transitions. So the research in these direction is still on. And portfolio optimization problem itself, find the best solution out of possible choices. This is a very important one because you use it not just for selecting your stock, you use it for your energy grid optimization, you use it to optimize your vehicular traffic. So while this looks trivial, it plays a role in our daily life at very unexpected ways. So thank you so much for listening. This is the last thing I wanted to talk about. And to quickly summarize what all we learned, first we explored the variational algorithms using the analogy of what if you're trying to hike from the top to the lowest valley. So in order to find the lowest valley, you will try different trajectories, try to take neighborhood trajectories to what you already tried, and want to keep only the best routes for yourself, which take you to the lowest valley. In QAOA, on top of this approach, you have fixed number of checkpoints. Your stride length is fixed. And now you try to parameterize how many lefts you want to take, how many rights you want to take. But you have a fixed number of layers.
Mm.
And on top of it, when you apply CD corrections, it's like you found a level ground you ran. You have to make sure you're not running in the wrong direction. So you use your poles to correct yourself. And there are mathematical formulations for it. So check out the paper I mentioned. And finally, we came to the problem of portfolio optimization, which is same as packing your bag, by the way. You have to choose your best possible options, given the correlations between the different items you want to take, how risk averse you are, what's your budget, what's the weight of your bag. And we saw that these models can be mapped to Ising-like model or quadratic unconstrained binary optimization model. Why? Because all of these we formulated as yes, no, right, left. Should I buy the stock? So always you have binary variables. And of course, you can solve it using many classical methods, but also quantum methods are nowadays doing very well, and using CD corrections, the results are much more improved. So I hope you enjoyed this hiking trip and packing your bags. I'm happy to take any questions you might have. Thank you so much.
Bravo. Thank you, Mona Lisa. This was very clear. I love your presentation too much. I have one question for you.
Yeah.
For the last paper that you present,
Yeah.
the CD part, you use exactly that you showed before, right?
Same circuit, yes.
Yes, because as I understand well, the CD part has to be adapted to the problem.
CD part to be?
Have to adapt to the problem for the specific problem.
Yeah, of course. Because, for example, sorry?
So we have to change, for example, if I change a problem, I have to adapt the new expression of the CD part, right?
Yeah, of course. Let me actually go to a formula. So, like, you're absolutely right. Thanks for pointing that out in case it was not clear. Thank you so much.
Oh, it's clear.
So here, if you look at this equation is actually from Michael Burry's paper in 2009. So here, Burry hasn't even told you what's the Hamiltonian.
Yeah.
Here, H can be in X, Y, Z, whatever direction.
Mm-hmm.
So depending on the structure of your Hamiltonian, or suppose if you have interaction, you will construct an effective magnetic field, which has all the XYZ components. and you can exactly calculate your CD term here. So as long as you know what your problem Hamiltonian looks like, of course, there's exact formulation. But in practice, we generally cannot use this exact formulation. So this solution, this is by considering that your H is only in the Z direction. And you have a mixer Hamiltonian, remember, 1 minus alpha Hx.
Yeah.
So it's using those parameters. But this is an absolute calculation which we did. So the problem is, suppose in your problem Hamiltonian, you have interactions between all n qubit. In that case, if you are to write this expression, you will have n string operator corrections. Like here, you got away with just using a y. But here, if you solve this, if it's an all-to-all connected circuit, your string length is n number of qubits, which is extremely expensive. So even if you could use exact CD correction, it's not feasible. The noise in your gate will kill you. So you always try to even use an approximate term. So if you're really interested, just search nested CD correction. So people right now have given different formulation as to how you can approximate your CD term from here. When I say approximate, it means it will have a lot of error, but you can choose how much error you can okay with.
Wow.
So that's a solution. Like there
Yes,
is an exact formulation, but it's costly.
very clear. I have one more question because okay, we use a CD path to go closer to the correct answer, right? So in a paper, how many qubit? Because it depends on the asset. If the system grow bigger, you will not able to use many qubit, and in this case, you cannot will not able to use many layers. So in the article, how many qubits they use? The system as big or not?
This is not big enough, actually. You're right to point out this is not big enough. But what I did not talk about today is there is a digital version of quantum annealing.
Yeah.
So in that digital version of quantum annealing, it's called DCQO, Digital Counter-Diabatic Quantum Optimization. Using that, people have been able to go to bigger number of stops, for example, 24. But you're right, using just QAOA and just CD correction, probably not even that. So the number is not that big yet, but it's already a much more improved version than what we had. So why should we keep trying it, actually? The hope is that when we have fault-tolerant computation with actual error correction, then these errors will not stockpile. Then we will be able to use bigger CD terms, actually. Because if it's a truly error-correcting hardware, then we have to worry less about errors and we can scale up. And there is a hope, actually, that maybe with large enough number of qubits, might be able to beat the classical method. So for example, this year IBM released in March or April the decathlon problem set. So portfolio optimization is part of it. And there's a specific result. It needs verification. But the result is that if you are able to do around 1250 logical qubits, then the speed of reaching to the solution, actual wall time, might be faster than your tensor network kind of problems, for example. Because remember, these are finance problems, vehicle routing, all these problems like to be done in small time. Your wall time matters, how many seconds or hours you took to the solution matters. So while we have a problem with number of qubits, as long as you're faster, it's still good enough.
Thank you. So is there any question on online, on site? So thank you, Mona Lisa. Thank you. If
Thank you so much for listening.
Mona Lisa, please ask on Discord and Mona Lisa will help us to understand
to answer the question. Thank you again.
Thank you so much, and thank you to all the organizers.
Thank you.
More power to you. Take
Yes,
care.
thank you for your support. Thank you.
Bye
So
bye.
yes, thank you. We're moving.
There's a question, I think, from
Yeah.
JL. Jinu Lee, do you have a question?
Please proceed.
Oh, okay. Proceed. Okay. So goodbye then. Thanks, guys, for listening.
No.
How?
I mean, please, Lee, you have some question, please, please ask. Gino Lee, you wake up.
They're tired from the hike. They can send questions later, Ben. Okay.
So, thank you, Mona Lisa.
Thank you so much. You guys have been awesome. Thank you.
Thank you. So we're moving on the hand-on exercise for variational algorithms. Please join me in welcome PhD candidate Lee Duk-chuen from Riken, Japan.
Hello.
Yes.
Okay.
We can hear you. Yeah. Say a little bit louder.
Okay. You see my screen?
Yes, everything is okay. Please start.
Okay. So hello everyone. Thank you very much for Mona Lisa for her very wonderful, intuitive and wonderful lecture. So hopefully you guys get familiar with get the view of what the variational algorithm or QAOA algorithms. So now is the time to get your hand dirty on the exercises sessions. So before we move forward, I would like to use some few couple of words to introduce myself first. So my name is Lee Duk-chuen. So I'm a PhD student at ITOM Riken, Japan. So my background is about theoretical physics and high energy physics. And currently, my research topic about quantum computing, quantum algorithm for quantum field theory. And if you guys have any intersection or any idea topic what you would like to discuss with me, so drop me a line in the email here, or you can just my name directly in LinkedIn. So okay. So I drop here some useful resources about variational is introductive and also quite tutorial notebook for you to learn from IBM Cloud and IBM Notebook. And please access here to run the notebook I prepare for you guys. It also have some guidance to install some packages needed to run the notebook. Okay, so the purpose of my notebook is try to guide you through how to use Qiskit packages to implement variational quantum algorithm and understand the variational algorithm workflow. Because why when you come to quantum world and you get the win of a variational algorithm everywhere, you heard about variational algorithm everywhere. So why so prominent? Because the variational algorithm can make can make use of make you advantage of the hybrid loop between the quantum part and the classical part. And you know, the current our quantum computer is noisy, so that's why we cannot run the full quantum algorithm like SOR or Grover. And even the full quantum algorithm, they also transform to the versional version to run on our current noisy quantum computer. So it's the best way to take your first step into the quantum world is to learn about variational quantum algorithms. And the first useful application of variational algorithm, maybe you quite interested in about the optimization problem that Mona Lisa gave us a lecture about, and we're using QAOA technique. So this is the chart about the workflows of the variational algorithm. Especially is variational engine solver VQE. So it's a hybrid loop that make advantage of the quantum part and the classical part. The quantum part, we try to implement the quantum circuit in the quantum computer, and we run and collect the data from in terms of bit strings, and we use the classical computer to do the optimization, to do some tedious some calculation work is where and the classical computer is quite powerful now in that part. So, and after optimization, we get the optimal parameter and just feed back to the quantum part and just run in the hybrid loop, because hybrid means the quantum and classical in combination. And the variant of variational quantum algorithm, the difference is from this part. Mainly from this part, we encoding the problem to the Hamiltonian. So like QAOA, the optimization problem, this part also costs your time the most. Yeah, because in Qiskit, we have the function to deal with this part. Basically, you just feed the data in and run, and then you get the result. But this part you will have to do by your, manually do, or actually there are some function helper to do it more quickly, but basically we have to brainstorm about this part a lot. So I okay. So this exercise, the purpose is I would like you to have your hand on and get familiar with how variational quantum algorithm work. So the first exercise, the first and the second exercise, I let you to do some very basic one about a variational algorithm. Try to build a cost function for the hybrid loop, because if you run the algorithm, you do the optimization, you need the cost function. It's like in the machine learning, if someone in the computer science. So yeah, so I let you to deal with some very simple Hamiltonian and build a cost function, and then we will move to the interesting part about the optimization problem. So indeed, variational algorithm can we can use it to deal with many optimization problem like travel salesman problem or scheduling problem or the portfolio optimization problem that Mona Lisa mentioned previous, and also and here I let you to let you to deal with the simple mascot problem. So the mascot problem is if you have a graph, you try to cut the graph into the you try to cut the graph into the different parts, separate the graph, and the cut your cut will be cost depend on the weight when your cut cross. So each line in the graph will have their weight, and when you cut the graph into different parts, and the cut will cross some line, and the total weight of the crossing line will be your value of the cut. So that's, and we try to cut the graph in the maximum, just in the maximal value. So probably is the mascot problem. So the exercise 3 and 4, we will get the idea about what is the mascot problem and how transform the mascot problem to the QPO problem. So what is QPO? QPO is the quadratic unconstrained binary optimization problem, and this form of the quadratic optimization problem can be easily implemented on quantum computer. And this part is, I mentioned before, is about the encode the problem into the Hamiltonian. I mean, yeah, that we can implement on quantum computer. And many variants of variational quantum algorithm. The difference is just about the encode the problem. So and the next part is from the QPO. When you have the form of QPO, you need to transform into the Hamiltonian about it. Like spin, Mona Lisa also gave us a lecture about that. So from the QPO is just the equation. So how you from the equation to the Hamiltonian with the spin Pauli ZX matrix, and from that Hamiltonian you can use the gate, the quantum gate in quantum computer to implement, and then and finally we'll run the QAOA on Qiskit, run the hybrid club I mentioned before. That Qiskit already provides us some function to do that, so it's quite easy. Yeah, and the final is extra exercise is for one who is already professional on quantum computer, on variational algorithm before. So try with different answers, with different hyperparameter to see the performance of the answers. Okay, so I think that's all for the first part, and see you on the next part about the another variational algorithm, SQD. That's very that is a very prominent technique we use in quantum chemistry. And yeah. Okay, so if you guys have any question,
no, it's fine. Let's practice, and then if we have some question, we will ask Qs on Discord.
Okay, so I will come back maybe 20 or 30 minutes and show the solution if will be needed. Okay.
Yeah. Thank you, Lee. you have some question, please ask.
Yeah, sure. Yeah, we found the difference.
Yes. Yeah, just a few words on this. The people from US children. Together can reach. There are many projects so progressive. So that's why the way we got a simple price. Because we have a lot of that I could try to improve our okay. That's why now we just run on a loop. And it was great to feel like
Me, I think I'm not very good at organizing event or creating, yeah, in the project, because, and also like in the project I have time constraints because I study and I also work. So if there is something very specific, like I can work on, I can like look at the problem and see if I have my expertise and I can actually work on it. So I would love to do in the healthcare because I'm trying to get a PhD. So it will help me build my portfolio and it helps you build your like the projects or fine tune on that one side. So yeah.
And guys, okay, for the band over here, first, asking other people. So after the, and I try to structure my, it's not to do with a specific, but they were collected, for example, creating and in the company later, you could actually keep it off, but yeah, finding the people or the rest of those. So we're not be alone, but I'm going to try to do time with each other. Just for example, for this one, create a content. Or like the idea you see the books. And then you like what I mean.
Yeah.
The or have some paper living, for example, sure I have a weather and they want to from Korea to model something on China.
Yeah.
All the this require the expression of the ask you to do something for nice so I don't like what
Yeah, so that always has to be good.
so I would like to our goal to become about this if you are interested.
Yeah, I am interested, but I think next 6 months I do have a lot of time constraints. Like if you're organizing or doing a project and you expect me to spend some time, it's
I think until the end of this year will be on the meeting videos. Videos. How you always need this life to that how we can structure the community first.
okay.
Then it like for example January. We are not like so okay you see what like another time or you don't know how it's like. That's the only way how we define. Let's see. I think I want to guys. The guests are very positive. You guys very soon tomorrow as well. Very big potential, but we can want to do something more interesting or better. That's one hour you can see we cannot control how many people come because they are reaching certain day too much because we want to connect and share different one like to HR
to request for to because there are two member our team trading just only two members for
So not joining and everything. But let's say like Jan to August, I'm actually self-constrained at the time and I do not have time to participate in all the events. That's okay.
learn how to
Okay.
nobody can. So the idea I will be here, I will be in the middle of all the event. So so if you can see there are only 5 people participate on the Qiskit podcast now. But reality we haven't ever. So that is our choice to participate. You have to handle with this.
Okay.
But I cannot like serious like because everything is no profit and what it's very difficult like is some people can always say I want to do this but way after this as well there are few people that don't know how to do what everything so that's why more only that safe. I will be not like this, you see. We try to learn from this mistake, but it's not really the mistake, but
Yeah, it's out of your control, right?
nobody. So you please take time to tell me
Yeah, sure.
because you are so talented.
Not really.
Because you're looking for really let us everything. So that's what we want to do. Lot of option. Yeah, manage hackathon. I will feel like a last step. Not have a very good model. Try to work out background and then we become stronger.
For the moment, like until I have my priorities, you can send me a text. Like if you want anything from me, you can send me a text. You can ask me anything. If I have time and I don't disappear. If I take a task, I will complete it. Like really complete it.
It's just
So you can send me a text anytime. I can introduce myself. Maybe to join me maybe. But yeah, you can just send me a text and okay, are you like available from this time and this is the workload. If I can take it, I'll do it.
because there are many people who are not available for now, but they still help us. For example, mentally or on that with you.
Yeah.
The idea is not awesome because that is again. So I will not be this guy. To help the community is not belong to me, it's belong to so we have a lot of potential now we can have something.
Are you going for the IQM hackathon? Spain? Is your team participating?
Yes, that when
It's December.
December.
Yeah, you have to be there in Madrid. That's why I do.
In Madrid.
Yeah, good.
Where? So yes.
Should be open, but I don't. Yeah, and they're giving access to the hardware, so I was very excited. It's open. Yeah.
How many days?
So it starts next December, into next month.
When is this? I can go. Let's discuss after that. This event. Check when it closes. I will add you to my community and then you can add the hackathon. I'm willing to join with you.
I think it will close when it reaches. It's on the weekend. Okay.
Will be very difficult.
Mm.
You know, we did it with very few team members. We have the chance. Never win it.
And I went alone, you know?
Yes. You see?
Yeah. So let me know if you're coming to this hackathon.
Just send me this. I think if you, I will add you on my team.
Yeah.
But until the end of the week, I will run our strategy.
Okay. Yeah, because this has a healthcare, it has a healthcare challenge, so I think it would be good to get access to their hardware. For 25.
But I care too. Because of yeah, I will see. I will answer you tomorrow.
Yeah, no worries. My tickets, flights are booked. Hotel is
But I
booked.
want to,
You
I want to
have
have
to.
you.
You need
Because
to
you
tell me.
know about my team, so I have to have you.
Yeah, you can tell me if you are going there. And the good thing is that you don't have to register in teams. Like you can just register individually, go there, and you select a good, you know each other. Yeah.
So the hotel will be over, or we have to
No.
pay anything.
Accommodation flights are.
I think it's okay. I have to check with my.
Flights are not cheap. You have to book a month ago. I waited 3 days and I had to pay 10 euros extra. So make sure check that.
Yeah, but I used to travel to Madrid. Why is so expensive?
How much do you think I paid for the round trip?
100.
No, 40.
Yes.
Yes, that's the benefit of early bird. Paid 40 for my flights. Remember, around. That's what you get.
I will check everything.
Yeah. Okay.
So,
For me, I will leave now because I have RERB issues. Like I have to travel. I'm going to do my hands on this algorithm because I already worked with them. I'm working on quantum annealing.
I see.
Yeah.
You're able to work on quantum machine learning.
I'm trying to use quantum annealing to find the global minima in non-convex spaces.
Yes.
Yeah, so that's one of the major bottlenecks of classical machine learning in non-convex spaces. So I'm working on that.
That is our personal project.
Yeah, my personal project.
So we can come up.
Okay.
I focus on this too.
Okay.
Because right now we have a different kind of classical optimizer, but they are very expensive.
Yeah.
We can. That could be one of the project when you join the team.
Well, that's interesting. I'm actually working on a proof of concept to get the launchpad from D-Wave.
Yeah, okay.
D-Wave gives the launchpad, but you have to tell them the project and for 3 months. If you use D-Wave, like
I
this
use
the
for
launchpad.
recently for quantum use. So I know how to use it, but it's very powerful.
It's very powerful.
So what we have to do, we have to build a project.
No, it's just that you have to give them a proof of concept, like what you want to work on.
So that is the project.
Yeah.
So in case. Because it's not only to be part of. Yeah.
I like
To prove the concept and then they give us a free.
yes.
So we have to queue all the bus the same.
But I don't want the D-Wave launchpad now because I have 3 hackathons. So I can't use that properly, you know. I'm participating in the QIA next week, Quantum Internet Hackathon Span European.
Yeah.
Next week. Okay.
See, and this weekend I actually go to UK if it's on single. So you have to pull for this month.
Okay. Yeah, so for me this month is full in December because of these 3 hackathons. So I'm working on
No, you can work like more step every day and then share the then they can probably do.
yeah.
So do not do not go down words both and both then or
Okay. Yeah.
For classical optimizer, that is a very good.
Yeah. Yeah, I guess. I have started working on it, but I'm working more on the molecule side. Like I was working with molecule classification, but I will focus now on the machine learning part. Let's make sure this project.
Just the machine optimizer.
Yeah.
So I think it's more about mathematical side.
Yeah.
Do you see on the Qiskit the book? Because I saw it for it's called classical optimizer. There are many methods. There are nature right here.
Reading these things. Yeah.
Otherwise, there are many things.
Yeah. I'm gonna check on it.
So there are you can see it and you can check it, but nobody will do it together.
Okay. That sounds good.
Yes.
Yeah.
So thank you. You.
Thank you.
Please come in tomorrow.
Yeah, I'll come. I'll come this week. Only Friday. The first part I cannot.
Can you bring some here?
Yeah, I think I have one person. Let's see if he will come. He's a software engineer, but he's interested in quantum.
Bring any point because now tomorrow is very bad for the company. They see it, but
they will not see that very few people, and then the next time will be.
Yeah. Well, it's a short notice. I'm not sure if his schedule is free, but yeah.
Try your best.
Yeah. Sure. Yeah. You for organizing. What is this hackathon you're organizing on Friday? It's just like 2 hours?
No, it's I think 2 or 3 days.
Oh, okay.
Yeah,
So Friday you will give the problem and the deadline will be like Monday something.
exactly. The machinery, random walk, and question.
Okay.
So it's quite a big, but we will not dense enough to have a bigger event because we have some more learn and then for everything. But the idea I want to do something that's more interesting for the hackathon and bring more money and do something very creative. But even this one will be very creative, but I cannot bring as money as I can. So, yeah. 2 weeks ago, there are no students. Not sure. What happened? They're doing everything.
So that's learning to come speak.
Yes. Yeah, but we are not lucky because that is the end of the year, so most of the company don't say about this. I think the next time we will organize a big hackathon. Not the course, we try to organize a workshop course, then hackathon with the hackathon purely, but hackathon feeling. This day, I can bring the modules, I can bring the files. I just how to would plan to go on it to come. And I think that is more than so many work to invest.
Yeah, but like generally, if we see in quantum hackathons and workshop, people are very less. Q-Poland was global, Q-Hack is global, but how many people were there? You saw yourself, this is 24. So you don't have to think like you did not organize well. They are international. Q-Poland, like Q-Hack is so international, like, but imagine how many teams participated globally. 24. Just 17, 24 people in total international. And you're thinking France. Now we are talking France. So you will obviously have less in this field because a lot of people are afraid.
I think the biggest success that we have a online tour.
Online, yeah.
Okay.
Yeah.
Because I want to meet the company president because I want to have a further collaboration. America provided for the collaboration. You can contact them or getting for the answer. If you come in front of them, okay. That is the way that I bring forward. So for the reason I want to organize something unique. You see, it's not only opportunity, but also finding talent, remember who are highly interested in the community. So I think it's only something. Strongly believe that because most of my team members work very hard and they will go to continue have a very good talent. For example, this guy from American, but tomato for it, that was very much. You see, they're like as because business and yeah, our sunshine. We just need to because we are feeling a bit it by each people give and do something more than here. Sure. Make something like that's like for the investment. But I was not able to prepare well because haven't organized and also with personal reason. What to make on my house and how to handle with it. I was so bad. But we were actually that toxic. Yes, and was the only one who has the result of work on the energy and then like 3 years, 73 and then put some of the money. Once on the point that we get with the investment, so close that
You should also know that I'm very good at public speaking and I can create business pitches like this investment pitches. I have 3 years of experience. I worked in an entrepreneurship cell in my college. They even call me for investment pitches. Also, I can get you. I can surely get you. Like really.
yes, in your community as well.
Yeah, I know how important the investment pitches are. They kind of want a storytelling aspect. They want to know what kind of profits they will have. They want to know like when they will have this breakthrough curve.
We did not have this experience.
Yeah.
But still, we did not have enough time to prepare because Qiskit was just take me a lot of time.
Yeah, I can understand.
But you see, in the future, 2026, now 2025, we need to summarize everything. Discuss what we can improve. We change the structure. Based on these things, we have an MIT that we completed, we try to run on a hardware. And I think after a few months, we can get something very interesting. Every event, I think we can organize 1 or 2 one-on-one Pittsburgh, one in the summer.
The one you know?
My wife.
Oh, okay. Important.
Yes. It is the reason I'm busy now too. That's welcome.
Yeah, I am.
See you tomorrow.
Yeah.
Si vraiment tu m'as dit, ouais, tu vois, aujourd'hui, si t'es pas là, je suis dans la merde. Ouais, c'est ça. Ouais, tu vois, je sais pas comment Pouna, il a mal.
Ouais, il a pas d'explosion, mais
Là, j'étais calme. C'est bon.
so
I mean, it,
I think we see.
I can ask Chuan to come back and then he present the next part.
Yes.
Everything is okay?
Yeah, I'm working my way through this
You
flow.
understand the concept?
Roughly speaking, like I need to.
Okay.
Yeah, I mean,
Okay. You are advice.
well, I'm making progress. I mean, I understand the. I think I understand the basic concept of. I understand what he's trying to.
Everything,
Okay.
every algorithm run on the same way. Into the age of innovation, transformation, and
Okay.
quite different. But the power of quantum algorithm that won't run for the same concept. Okay, for example, you have a classical data. See, you want your quantum machine to understand your data. This way, first, what we have to do, you have to encode
Okay.
the data into the block sphere.
Yeah.
Because why we have to do this? Because we want to explore bigger hyperspace as possible. Because if you can explore bigger hyperspace, it means that your solution would be better because it's taking into account more options.
Yeah.
You see what I mean? So the data encoding method, there are several. So the only thing that you have to change a little bit, every single problem you have to change different data encoding. Secondly, right now, you just encode your information. What kind of algorithm you want to do? You see? So this depends what kind of problem. You see? And you just the most common way that you turn the problem into the Hamiltonian and try to use, for example, some ansatz, the typical ansatz, in order to the quantum system understand what you want to do, you see? And then after that, you do measurement because, quantum computers do all the work. And now, in order that you can understand, you have to measure because if not, you will not. You see?
Yeah.
And then you measure, you get the results. Okay. And most of them use a classical optimizer. Yeah. Because for example, for quantum optimization, you want to reach the state that your information is in ground state.
Yeah.
In this case, your information is good. If not, this was not the ground state, it's a second state. So the information is not judged. You see what I mean? And in this case, we have to use a classical optimizer to find the minimum of the landscape.
Yeah.
You see, so that one. So in this case, for the classical optimizer is classical part. There are many methods to minimize the landscape. You see what I mean?
So for all of them, it's like this. For the quantum machine learning, it's the same. But the
Because I
different,
have only the engineering background.
different that's in the beginning, in the middle. You see, and they all run in the same way. So that's why, if you understood and you understand the variational algorithm, you will be able to understand everything.
That's very good. Yeah, I have to take a bit more time to go through.
So when that's you time, if you need some help, please, I'm here.
If I have questions, I will ask. Yeah.
Thank you. Hello, Trương. Hello, Lee.
Yeah, I'm here.
Yes, can you please present the second part of your notebooks?
Okay, sure.
You have first show the solution. You told me. Do you want to show the?
Should we? Okay. Okay. Show the solution first.
Yes, I mean the selection you have. In first one, like supervisor has three for this solution. So that you have one study.
Could you guys see my?
Yes, everything is perfect. We cannot see on this screen what happened.
I saw it turn off signal. Maybe you for a long time sharing, so it just turn off. You talk something.
No. It's not turned off. Momo? The screen is off.
Yes, we need to share the screen now.
We share the screen, but we cannot see here. We can see on our laptop, but not here. So please let me check the program.
No, you don't need substitution. Substitution. It's like what? I know.
I just went master.
You did one master. Yeah.
For the PhD position.
Il était éteint jusqu'à présent? Vous l'avez pas utilisé?
Non, ouais, on l'a partagé l'écran, mais ça le. Il était allumé, mais après après quelques temps,
Il s'est mis en veille?
il s'est mis en veille. So, il faut appuyer, c'est ça?
Peut-être. On va voir.
Okay. Maybe
Yes, I was Spain. Turkey.
let's
5 years.
Oh, it's complicated like that.
Before sharing their solution,
It's complicated.
is anybody on Zoom have some question to ask?
Yeah, but
So before, oh yeah.
this you don't need
No signal.
là, they need to
Deux? Ouais. Voilà.
Merci.
Je t'en prie.
So we're ready, Lee. Can you share the solution?
Okay.
I'm not working in the university, I'm working in the but my contract is with the university.
Okay, so this notebook gives you a detail that I haven't mentioned in my talk in maybe some aspects that did not be mentioned in the Mona Lisa lecture. So you can have a read through this notebook. But here I will quickly go through the solution for the exercise first. So the first and the second exercise, you try to get acquainted with the basics routine of variational quantum engine solver. So the first exercise, so in the exercise one, we try to build a cost function using primitive estimator. So basically, what you need to know is about how to use the Qiskit package to run the circuit. Yeah. And feel free to stop me at any time you have a question. Okay, so after you know how to run the circuit on the estimator using estimator and sampler, yeah, there are two primitive to run the circuits, the estimator and the sampler, and this notebook help you get to know that. So in the exercise, in the second exercise 2, we try to a different Hamiltonian is a combination of Pauli Z acts on the first qubit and the Pauli Z acts on the second qubit. In the first exercise, we work on the simple Hamiltonian with Pauli Z, just one qubit Pauli Z, and it's quite simple. But how about we move a bit forward, about 2, and the difficult part here is we use the sampler to compute. I mean, we need to know how to compute the expectation of Pauli Z terms. In the expression of probability of the bit strings when you use the sampler to get the proper probability of the bit strings, and how from that probability you can convert, use them to compute expectation of Pauli Z. So I think that's the difficult part, of this exercise. And just run again, use the same procedure. So this is the answer for the problem. So I think I saw somewhere that's how we get the formula, but you can prove it by is this the answer? I think I give some. Oh, here, yeah, you can use this formula. Mean Pauli Z. We can explain into the brackets of 0 and 1, 0 and sorry, this would be 1. Yeah, 0 and 1 vector, and if you substitute this formula into the expectation here, the one prerequisite of knowledge is you need to know how to manipulate, how to deal with the brackets algebra in quantum mechanics. So yeah, so I think that's another thing you have to know. But if you substitute the formula I provided above, so you can get the how you compute the Pauli, the expectation of Pauli in the big strings probabilities, and that's also applied generally applied to the more complicated Hamiltonian involved mainly Pauli terms, ZZ term, even S Pauli S term, Pauli Z Pauli S term, so on and so forth. Okay, so after you run on these cells, you will get idea or maybe a bird's eye view about how to use Qiskit to run rational quantum algorithm. And next is about the QAOA, the quantum approximate optimization algorithm. And as I mentioned before, there are many optimization problems that we can try. And in this notebook, I just try to solve the Mascus problem, but you can use the same procedure. But as I told you that the different and also the difficult part is how you formulate the problem into the Hamiltonian, the cost function, scheduling, snapback problem, and portfolio optimization problem. How we can implement, encode the problem function or problem equation into the Hamiltonian or the cost function that we can implement on quantum computer using the universal gate, using the quantum gate. That's the problem. And okay, so first, before we move to the quantum approximate optimization algorithm, indeed, from the current procedure that you may not know that there is some we just in the current lecture we just omit, some part we omitted. We can directly start from the problem to the circuit, but indeed the underlying background, the underlying knowledge, how we can map into the problem into the quantum circuit. So that's the QPO or quadratic program. So you start from the optimization problem, and any problem you want to optimize, and you have to convert it into the quadratic program, and then from the quadratic program is specific. Not all quadratic program we can implement on quantum computer. There's one specific one that can easily implement is QPO. It's a quadratic unconstrained binary problem. So that's this notebook will give you have a view about what's a quadratic program optimization and what is and QPO is just a one specific one specific example of quadratic program. Yeah, and how we can formulate math problem into a QPOL. So yeah, this is a graph that you can cut into a different part. So the white part involves 2 nodes here, and the black part involves 3 nodes here, and the weight, I mean the value of the cut counts the weight of the line, the connecting lines here. So each line will have each line will have its weight. So when you cut cross the line, so the total weight of the crossing line is the value of the cut. So we try to how we can cut to maximize that value. So we formulate the cost function, I mean the value, and then from the value we can see the form of the quadratic program. Yeah, and start from okay. So this one is we try to build the quadratic program from the Muscat problem. Here. So there's some function that we can make use to get the information about the graph, and we can get the weight and also the node, so that we can build the quadratic program. Quadratic problem.
Si on fait soit. J'ai dessus.
And then we plot on the possibility of the cut. So 0, 1, 1, 1, 0 here is on this thing is just about the it's very thin the cut. For example, here you see 1, 1 in the nodes, first node, second node, and the fourth node. It means the cut will separate the one, the second one, the first one, the second one, and the fourth one into one part, and the third part and the fifth part into the second region. So, and the higher is the cut value, and you see this four is show us the higher cut value is we just try to this because it's quite a simple problem. The space of all the possible solution is quite small, so that we can try to see how the value of each cut should be. But in the very large graph, in the complicated graph, that's impossible to draw this plot, and it's also intractable in the current classical computer. So that's why that's the space that the quantum computer can jump in and make a lot of interesting things. Okay, so yeah, it's like a quadratic program, and from a quadratic program I said before, the QPOL is just one simple quadratic program, and this line below is just trying to start from the QPOL from the graph to build the QPOL of quadratic program. It lies similar to above when we start from the graph to the quadratic program. Okay, so so if you can see, so actually the QPOL quadratic program, the two important as a matrix in, the parameter is this Q matrix, and the Q matrix is nothing but the weight. This matrix is the weight of the connecting line of the graph. So we can use we can get information, extract information, and construct the QPOL program. And how to construct the QPOL program or quadratic program that in the above cell, in some above cell, I let you to get familiar with in the above line. So just scroll up and try to play around. And here, yeah, we use the quadratic program, the function from Qiskit package, and input some information. The QPOL matrix that I mentioned above is nothing at all but a weight matrix represents the weight of the connecting lines of the graph. So after we we get the QPOL operator. So is the QPOL operator how the QPOL operator from the Hamiltonian? Okay, so maybe you see so many steps, right? But actually is the grounding. I mean, yeah, it's a starting point where the people try to use quantum computer to apply in the optimization problem. That one very routing point. So we after we have QPOL, it's quite straightforward to start from QPOL to the Hamiltonian with the Pauli Z, Pauli X, Pauli Y matrix. And one thing I should mention that in a quantum computer, the Hamiltonians should be expressed in terms of Pauli matrix or the product of Pauli matrix that we can use the quantum gate to implement, because basically the quantum gate is just the rotation of the rotation generated by the Pauli matrix, like rotation of around the z axis. So it's generated by the Pauli Y and rotated about the axis generated by the Pauli Z. So to encode the problem into the Hamiltonian, basically it's just how to use the Pauli matrix to express your problem. So from QPOL, it's straightforward to transform to the Hamiltonian with the Pauli Z here, you see. And as Mona Lisa gave a lecture about that, so you see it involves two layers about our problem we call SC or Hamiltonian cos Hamiltonian, and some how to say I forgot her words is, but it's inspired by the adiabatic evolution. When you have an initial Hamiltonian that you know exactly the route state, and our cos Hamiltonian that we want to identify the route state. I mean, the route state, it means the solution of that Hamiltonian. Yeah, and when we optimize when we figure out the solution of one optimization problem. But nothing at all. But we try to find the route state of a Hamiltonian. So a problem corresponds to the Hamiltonian, and the optimal solution corresponds to the route state. Because the route state here is at the minimal energy, and that minimal energy corresponds to the optimal value you want to figure out. Okay, so that's a hybrid loop, and that's why we consider it as a variational algorithm. Exercise 5. I go through exercise 4. Yeah. Okay. Okay, QAOA variational form. So on exercises below it, just you will deal with the QAOA algorithm, start from the build the operators and the answers, because here to build the answer, if you can see, we need the block gates. Here you need to know the information from the Hamiltonian, and if you start from the mascot problem to the and then go to the quadratic program and QPO, and when you have the QPO form, you build the Hamiltonian operators, and from the Hamiltonian and operator information, you can build the answer of the QAOA. And the answer is the feature of the variational algorithm. Okay, so that's the answer look like. So here I comment this line because in our mascot problem, the linear term is not necessary. I mean, it's 0, so you don't need to encode the linear term in the quadratic program. Quadratic mean okay. So here the linear term is this one. The C here is the quadratic term and this linear term. So in our mascot problem, the linear term is 0. So it doesn't matter. Okay, it's Hamiltonian for QAOA. So nothing, just how to use the Qiskit package. Oh, not really. Yeah, we need to extract the information from the graph, and then use the Qiskit package to build the Hamiltonian from the information from the graph. That's for the exercises. So the function spare Pauli operator is the Qiskit function that allows us to construct easily construct the Hamiltonian from the kind of the list. Thus you just need to denote the Pauli in the world, like you need to implement the ZZ Pauli on the qubits 1, 2. Yeah, so just write ZZ or and the index here, and even the factor of that poly, of that product of poly. So it's quite convenient that you just, yeah, you don't need to put the drop nickel product or and do the for loop. Yeah, it's quite crazy. So yeah, this function you need to just need to input the list, and from the list operator, this can help you straightforward to build a Hamiltonian. So exercise 7 is just the call function that you got familiar in if you run above cell, so it's quite simple. Yeah, it's just about how use some few code lines to run, nothing at all. Okay, so run, and then you will get the solution, the optimal solution, denoted as a purple pass here. Yeah, and visualize that is here. That's the cut. So the cut is something like here that separate these nodes into two regions. One is purple region, and the second one is the gray region. So some maybe roughly like this. So it cuts through this line, this line, this line, this line, this line. Yeah. Okay, and some Qiskit end-to-end QAOA class. That's a compact code that you just start from the yeah, I think just start from the graph and directly convert to the ansatz and Hamiltonian, and you run directly, just fill code here. You see, we try to do many things about a quadratic program, tuple or something, and convert blah blah. But yeah, just fill code right here. But I think you should know the underlying reason why we have, why we have QAOA, why we start from the optimization problem. We can build a QAOA algorithm, and it's helpful for you to determine all the variational algorithms or all the optimization problem. And then you can build your own code or algorithm for that. Okay, I think that's all. So I will share my next notebook about SQD. Okay. Okay. Okay, we done with the exercise with variational algorithms, and we move to next one. Okay. The next one is about near-term applications of noisy quantum computer. Is I intend is about the chemistry problem, simulating material simulation. Yeah, and SQD is quite a new technique. Was is quite popular recently, about used to in the molecular chemistry problem. Okay, so the learning objective of this notebook is about understand about the SQD methods, the sample space quantum diagonalization, learn to how to use Qiskit package to solve the molecular problem. So, but I will not get into detail about quantum chemistry. Maybe in the notebook we'll give you some view, some general view about that. But I think it's better to look at the IBM Cloud notebook or tutorial. Yeah, because it's a very big area to study. And then yeah, I think the main purpose of this exercise notebook is let you get play around with the choice of answers in SQD. Okay, so why? Because the answer in SQD is quite really important. That's the only quantum part. Okay, so we'll see the SQD is based on the sample space method. So what is the sample space? So here, let's imagine this matrix, the whole matrix here is the matrix of our problem. Okay, so when you have the Hamilton, like in quantum chemistry, in molecular problem, you need to compute the ground state of the molecular. So you have Hamiltonian. It's very same. It's very same in a matrix. So very large matrix with respect to the configuration of electron. So, but to compute the ground state of that, a very big space Hamiltonian. So not all the information is relevant. So we try to project the full Hamiltonian into a smaller one, and like the rough stack of the big one also have share the same information with the rough stack of the small one here. So the idea is we try to project the full Hamiltonian in a very big Hilbert space into a smaller one that we can easily do in the classical computer. So you see here is a wave function of our problem. So we prepare the wave function and try to get the relevant information in the wave function. Like the rough stack is just related to the low energy, right? So not on the information like the higher energy is not relevant. So maybe we just want to collect or to pick up some configuration, the lower configuration energy that's maybe more relevant to our rough stack, and start from from the space involving only the low energy configuration, and we project the full Hamiltonian into the small space of this small energy configuration, and in the smaller space we can use our classical computer to diagonalize, use the classical method to diagonalize, and we get the ground state energy, and that's shaded. I mean, at the same for the full Hamiltonian. So here you can see the subdict region here is the relevant information, and the cross region here is irrelevant information. I mean, irrelevant element. So we can drop. Drop, and you see just get involved this region, and from the full Hamiltonian, this region also the relevant one, when we just need them. Just get rid of the rest, and we bring down the full Hamiltonian into the small one, and use the classical method to diagonalize this matrix, and it's quite quick and straightforward to get the ground state instead of deal with the full Hamiltonian. Okay, so the SQD for the SQD step is we need to we need to choose the relevant configuration. So how to choose the relevant configuration? So the first step is we prepare the circuits or the answers, or we call the quantum circuit, that contain the information about the ground state, and then we run in quantum computer and sample, run quantum computer and measure and collect the sample bit string, and from all of the bit string, that's of course is respect to some symmetry, the given symmetry of the Hamiltonian line, the conserved of the number of electrons, and we choose from the measurement information, the bit string from the measurement and that's the relevant configuration we have, and that's contain the ground state configuration also. And we project the full Hamiltonian into the subspace of these configurations. So the first step, we initialize the circuit, use the information from our problem to construct the circuits, because that circuit will contain the information about ground state. If we don't, if we don't use the information from the Hamiltonian, we just construct the random circuits. So it's like you just random choose here. You just random choose the elements here, and maybe it's not efficient. So the control circuits gets information from the Hamiltonian. So in the notebook, you will have chance to go through the each type of circuit. One is from the random one, and one is from the informed Hamiltonian informed circuit, that we construct the circuits from the information from Hamiltonian, and you will see the better performance. Okay, so the step 2 is definitely the sample configuration in the circuits, and project the Hamiltonian to the subspace of those configuration. And step 3 is iterative process. So after you get the configuration, you project and you diagonalize, but you not stop there. You will do the another iteration. So it's called iterative progression. So what's the another iteration? So you will see here from the ansatz or from the quantum circuit, you get the bit string, the configuration. Of course, it should respect the symmetry of our problem, like conserve number of electrons, something in the quantum chemistry. And then, okay, it's kind of technique that's divided into the some patch. Yeah, like few patches. Okay, and diagonalize. It's basically just from the subspace of the selected configuration you diagonalize, but it's just divide into some different parts. Nothing. And here, the iteration I mentioned here is when you get the right state, and then you can calculate the so-called average occupancy. And from this occupancy, you can choose. I mean, yeah. In the beginning, I told that we from the configuration we will choose. We chose the correct bit string that respect the symmetry of the problem. But some configuration that have information, but maybe some error from the hardware that causes the big flip in that configuration. But how do we know that? So this iteration helps us to refine the result. So from the configuration that we consider is wrong, but we can identify the big flip information in the wrong configuration and correct that. So we will have another new configuration. So just do in the loop, iterative loop, and your conversions in the energy state will drop down, and that means you will get more accuracy. Yeah. So basically, you can see this AQD considered as a very small algorithm, but the loop is you don't see any the hybrid loop, right? Like from quantum part to the classical part and feedback to the quantum part. So indeed, it is because here you can construct your hybrid loop as also the extra exercise I let you to try to explore. So, but basically it depends on the problem. Some problem do not require you to build a hybrid loop. Just only start from the ansatz, get the sample bit strings, and do the classical loop. Here, you will get you can get the desired answer, but some problem, or maybe you need to build a hybrid loop between the classical and feedback again to the quantum answer here. So you will see the most important part of this method is the answers. So it's also the powerful of quantum computer here, because you see on the part is just around just about the classical thing. So what's the quantum here is it depends on your answers. So the ansatz is quite important in this method to make it a quantum algorithm. Otherwise, it's just a classical one. So that's why the purpose here, I would like to let you explore the different ansatz, and play around with that. So in the exercise 1S, the first few two exercises is try to get familiar, get to know the quantum chemistries and how to use some package provided by Qiskit to get the information and build the Hamiltonian from the molecular. And then the next exercise is play around with HUD and with different ansatz to see the different performance. Okay, so the exercise, because in the notebook I just show you the basics routine of the SQD, no any hybrid group that I mentioned between the classical and feedback to the quantum part. So just only one line from the So the exercise for anyone who is professional on quantum, so interested in explore the SQD, so try to build a hybrid group of the SQD. Okay, so I think that's too much for today. So if you have any question or you don't have time to finish the exercise within today, so just try to explore maybe next day or within this week, and drop any question in the Discord, and I always be here to answer your inquiry or questions. So thank you.
Can you hear me?
Yeah.
So thank you for the very well presentation about the notebook. And please, if you go practice, and if you have any question, please ask on Discord, on Team, on anywhere. We are more than welcome to answer the question.